Welcome to MathStat341 Probability Lecture 24. Years ago, a student had alerted me that they had to leave class early. And I said, do you want to have some fun? He goes, sure. And so, 20 minutes into the class, we had arranged for him to ask a really stupid basic question. I'm sorry. When you ask the question, you gotta go, get out. If you are this unprepared for class, grab your books and get the hell out of my class until you are prepared. He does a great job. He slouches down, and the rest of the class is just in complete shock. And then I go to everyone else and say, anybody else is unprepared or has a job interview in 10 minutes, you're welcome to leave now. All right, so last class, we did a lot of stuff. We did a lot of fast integration. Today is going to be a little bit slower paced. So the first is Markov's inequality. So I don't want to state Markov's inequality. I want us to kind of find our way to what might be a good inequality to have. And we'll have some many variable x with density f and finite mean expected value of x. And we want to try to figure out bounds on probabilities of events. The more I tell you about a distribution, the more we should be able to say. So all I'm telling you is that this distribution has a finite mean. And the question is, what's the natural scale to look at things? So maybe you might say it's reasonable to look at maybe the probability that x is greater than or equal to maybe some multiple of the expected value. So what's the probability that I'm twice the mean, or 3 times the mean, or 4 times the mean? That seems a reasonable question to ask. Now the problem is this is not reasonable unless I assume a little bit more about the distribution of x. So for example, what would be a really good or potentially really bad choice for the mean?
0?
Yeah, so if the mean is 0, then I'm kind of in trouble. No matter what I choose for A, I just get the probability that x is greater than or equal to 0. So maybe we need to assume the mean is positive. We'll assume maybe the mean that's greater than 0. What might be the problem with this distribution? So I'm assuming a positive mean, and I want to try to get bounds on the probability that I'm at least, so here's 0, maybe here's the mean, and maybe here's A times the mean, and I want to calculate what's that probability. It's going to be hard to get a nice answer. And the reason is, if I put a small amount of probability and a very large negative number, does that affect the mean? And I can make that probability as small as I want, as I move it further and further down to negative infinity. So if I move it very, very far back, it's going to be very small probability. I can have almost all of my probability up here. And so I can make this probability as close to 1 as I want. So we need to eliminate x being negative. So if we now assume that x is bounded from below by 0, now we can't move too far to the left. And now we actually have a chance of being able to say something. Because, if I want to get a bound, well, the worst I can do is put as much probability as I can at 0. I can't go further than that. And so this is going to lead to a much better result. So let's try to calculate what this means. So this probability would be the integral from a mu to infinity of f of x dx. Right? Do we agree that that's the probability that x takes on a value at least a times the mean? Now, we're going to do one of the most common tricks in mathematics. We're going to multiply by 1 in a clever way. This is going to be less than or equal to the integral from a mu to infinity of x divided by a mu. Why is that true? You normally can't just shove something inside the integrand. Why can I do this? Yes?
It's Because x is always greater than...
Yeah, x is always greater than or equal to a mu. X goes from a mu to infinity, so the number I'm multiplying by is at least 1. And it's never negative. I claim that this is also less than or equal to the integral from 0 to infinity. And I can pull out the 1 over a mu x f of x dx. Why can I do this? Because I'm only making things larger. I'm extending the integration down to 0. And the integrand is positive. Or the integrand is at least non-negative. Imagine I had negative values. Imagine x could be -3 or -4 or -5. Then if I went down, I would have a negative integrand and I would be making things smaller. So it's crucial in this argument that my density is non-negative. Do you recognize what this integral is? The integral of x f of x dx.
It's the mean.
It's the mean. So this is just equal to 1 over a mean over mean, or just 1 over a. So this is Markov's inequality. If you have a non-negative random variable with finite mean, then the probability that you're at least a times the mean is at most 1 over a. For what values of a is this useful? You need a little bit more than non-zero. So let's write it explicitly. So x greater than or equal to 0, mean greater than 0 is finite. The probability x is greater than or equal to a times the mean is at most 1 over a. For what values of a is this useful?
So 1 over a is bigger than 1.
Yeah, if 1 over a is bigger than 1, this is not that useful. Anybody have an event in the future that they care about, a sporting event? Anything? Yes. The game against Wesleyan.
Yeah.
So you have, at most, a 213% chance of winning. And I stick by that analysis. And if your coach wants, I am happy to walk him through my calculations, where I will prove conclusively that you have at most a 213% chance of winning.
Yeah, I like that.
Yeah.
Yeah.
Whereas you, for Wesleyan, they're getting at most 102% chance of winning. So I think we're in really good shape.
Yeah.
So this is useless if a is less than 1. It provides no information. And the way you can see this is, imagine you have a distribution. Here's 0, here's mu, here's a times mu. It's possible that all of my mass is at mu, right? That's a distribution that has mean mu. 100% of the probability is at mu. And then if I want to ask, well, what's the probability that I'm at least a times mu? I've got to get 100%. Because I know that's one of the possibilities. So the more conditions you have, the more likely it is that you're going to have a useful result. So this is Markov. And on a personal, right. Now, if I give you more information, the thought is maybe we can do better. So we have Chebyshev's inequality. So Chebyshev may be my favorite mathematician of all time. Not just because of the caliber of his results, they kick ass, they're wonderful, but because his name has at least 40 acceptable transliterations into English. So no matter how you spell it, it is almost surely correct. I've tried for years to get people to spell his name differently depending on which of his theorems you're talking about. If you talk about his theorem in number theory, you spell it this way. If you talk about his theorem in probability, you spell it this way. It's a wonderful, wonderful name. So what he says is, let's assume you have x. So density f, finite mean, and finite standard deviation or variance. So we'll use sigma for the variance. And then Chebyshev talks about the probability that x so there's a couple of things missing. What do you think I want to look at? The probability that x is greater than a certain distance from what value? Mean. The mean is the most natural value to be looking at. Let's look about what is the likelihood that we're far away from the mean? What units do you want to use to measure your distance from the mean? Standard deviation. So let's measure it as k standard deviations away. And if there's time later today, I'll do a little bit more on unit analysis. So this is the most natural thing you can ask. I want to be at least k standard deviations away from the mean. How likely is that? And it gets 1 over k squared. There is a more powerful version. If you know the fourth moment, you can keep going like that. If you know the central limit theorem, the central limit theorem often does better if x is the sum of random variables. But for many applications, Chebyshev works and is perfect. Now we'll prove Chebyshev at least 2 different ways. Anybody know what might be a nice result to use to attack Chebyshev? Markov, right. There was a reason when I erased, I stopped here. Right? Let's let y, so I want a random variable that's non-negative with finite mean, that's related to x and related to what's going on here. Any thoughts on what I should look at?
The A mu.
I'm sorry?
The A mu for
Well, I need to choose a random variable to apply Markov. And so I need to choose what is my x, and then what is my mu, and then what is my a related to here. So somehow y has to be related to x, mu, and sigma. Any thoughts what might be a good choice for y? Does x have to play a role? So I need something that's non-negative that involves x. What should I do to x?
multiply by constant.
So I could multiply by a constant,
Subtract the mean.
subtract the mean. So this is now, it has now mean 0. What should I do now? Because I need something that's non-negative. I could square it, right? If I square it, this is now a non-negative random variable. And what's the expected value of y? That's just the variance of x, which is sigma squared. So by Markov, we get the probability that y is greater than or equal to, now, what do I have to compare it to? The expected value of y is sigma squared. So let's compare it to k squared sigma squared. This is going to be at most 1 over k squared. But if I unwind this, this is the same as the probability that x minus mu squared is greater than or equal to k squared sigma squared. So that's just the same as the absolute value of x minus mu is greater than or equal to k sigma is less than or equal to 1 over k. So we actually can deduce Chebyshev immediately from Markov. We can also prove Chebyshev directly. There's no need, but I'd like to do it just because it emphasizes the argument we did in proving Markov. And when you have a good idea, it's nice to become familiar with it. So let me just adjust a bit. Okay, so proof 2. The probability that x minus mu is greater than or equal to k sigma, this is equal to the integral absolute value of x minus mu over k sigma in absolute values greater than or equal to 1 of f of x dx. Right? That's what it means to take the probability that x minus mu is at least k sigma in absolute value. And now I can play the same game as before. This is the integral, again, x minus mu over k sigma is greater than or equal to 1. And now let's just write x minus mu squared over k squared sigma squared f of x dx. And again, this is at least 1, so I can put it in. And then very similar to Markov, what am I going to do on the next line?
Inequality.
Yeah, and so what am I going to do?
You're gonna
Oh, so this should be an inequality.
extend the
I'm going to
bound.
extend the integral. And again, I can't go directly from this integrating over everything, because this is less than 1 if x is very close to the mean. But because I first do this only when x minus mu over k sigma is at least 1 in absolute value, this is true, and now I can extend the integration, and I only make things larger. So this would be less than or equal to 1 over k squared sigma squared, and then the integral minus infinity to infinity of x minus mu squared f of x dx. But that's just the variance. And so you just get 1 over k squared, the sigma squared over sigma squared cancels. And that proves Chebyshev. Yes?
Wait, just to clarify, how do we know that like this always extends the?
Well, because this is non-negative.
Okay.
So if I extend the range of integration, I can't be adding any negative numbers. The integration can't get smaller. So that's why.
Because f of x is non-negative.
Right, because it's a probability density. Probability densities are never negative.
Oh, and then the left side not. Okay.
Right. So what you can do is you can look at a couple of different distributions, and you can look at Markov, and you can look at Chebyshev, and you can do almost like a battle of the bands and see who does better. All right, should we do that now? We can either do it, or I can just give it to you as I encourage you to do it at home. Either way is fine with me. Do you want to do the battle of the bands or not? Yes. What distribution do you want to do? It's got to be a distribution that's non-negative, otherwise Markov can't even play. I don't want to show you ha 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 ha.
Is that already a law?
Right, because if you take something like the normal distribution, you can't use Markov. And so Chebyshev just destroys Markov. So we could take an exponential distribution. So we'll do Markov versus Chebyshev. Who do you think is going to win? Probably. Markov versus Chebyshev. We'll say x is exponential with parameter lambda. Now, let's take lambda to be 1. Let's make life easy. So the density is e to the minus x. What's the mean? The mean is 1. What's the variance, or the standard deviation?
1. It's also 1.
It's also 1. This is one of the reasons why I want it to be 1, so I don't have to worry, oh, is it 1, is it 1 squared? 1 and 1 squared are the same. So let's calculate, what is the probability that, say, x is greater than or equal to 10? By Markov, what is the answer? 1/10. So for Chebyshev, the probability x is greater than or equal to 10, well, this is a little bit annoying for us. This is going to be less than or equal to the probability, x minus what? Maybe x minus 9, no, x minus 1 in absolute value is greater than or equal to 9. But how do I write 9? I should really write 9 as 9 times 1, right? because the variance is 1, the standard deviation is 1 here. And so what do you get? This would be less than equal to
1/81.
1/81. So it's a decisive win for Chebyshev. Right. Let's actually calculate what is the answer. It's the integral from 10 to infinity of e to the minus x dx. So this is just e to the minus x with the order flipped. So it's e to the minus 10. Right. What is e to the minus 10? .00004, roughly. And if that's not enough for you, I think it's 4.5. So, we all agree Chebyshev destroyed Markov. And Chebyshev wasn't even close. Why does Chebyshev do so poorly? I mean,
Is it because of the number we chose as?
so you could do this for other numbers and other distributions and it's still going to be bad.
We're using 2 bits of information, the mean and the variance,
Yes.
instead of just the mean.
Well, that's why it beats Markov, because it uses more information than Markov. So Chebyshev beats Markov because it uses more information. But why do you think it does so poorly?
Oh, okay.
So you're close,
That's a different question.
but you're very close. Why does it do so poorly?
Because it doesn't have all the parameters.
Yeah, it only has 2 pieces of information. Imagine I'm trying to understand who you are, and I find out what your major is and where you're from. I can probably glean some things about you, but I don't think I would have a complete understanding of who you are just from your major and where you're from. Right? So the reason Chebyshev doesn't do so well is because it's not using that much information. The utility of Chebyshev, it's almost like the singing horse. What's amazing is not that the horse sings well, but that the horse sings at all. Okay? That's how you should view it. Chebyshev is, look, hey, as long as you have a finite mean and a finite variance, we're in business, I'll give you an estimate. But Chebyshev has to be open to all customers with a finite mean and a finite variance. Oh God, I gotta do you and you and you and you and you. So because it has to handle all those different things, its result is not going to be as strong as possible because it's not using a tremendous amount of information. But it's using more information than Markov, so you hope to be able to do better. And that's, I think, roughly what's going on. Now, we have not done Newton's method in this class, correct? So what I want to do now is I want to do Newton's method versus divide and conquer. This is going to be another battle. This is the problem that converted me from, I'm math and physics to I'm math. I'm going to go on and do mathematics. I did not see Newton's method until I was in college. It is one of the most remarkable things in the world. If at the end of this you do not have an appreciation of pure mathematics, I have failed you. Okay, the fault is definitely not Newton. It is all me.
What's the decision to write Chebyshev with an S on purpose?
Oh, did I write it with an S?
Yeah, you spelled it differently again.
Oh, I think this is just my poor spelling. So how many of you have heard of divide and conquer? This is one of the great algorithms of all time. So as an example, I need a volunteer who is willing to allow me to partially guess their birthday. Okay. Were you born on July 1st? Earlier or later?
Later.
So with one question, I've eliminated 50% of the dates. So July, August, September, well, July and August both have 31 days, so I'll go September 30th. Earlier or later?
Later.
So I'm going to stop after this so I don't give too much information about you. But with 2 questions, I've now eliminated 75%. So each question, I eliminate 50%. That's not bad. And so you can get anybody's birthday in 10 questions. You actually don't need 10, but this allows you to slip a little bit. You have a little safety margin. So imagine you have a function on 0, 1. it's continuous, and it's positive at 0 and it's negative at 1. What must be true?
It goes through the,
But it must cross the axis. It must have a 0. Why? What theorem guarantees the existence of a 0?
Intermediate
The
value.
intermediate value theorem. And if you want to see a proof of it, if you email me, we actually proved that in operations research, I think, earlier in the week. So it's got to cross somewhere. I don't know where. Let's go in the middle. And if you're lucky, it vanishes at a half. You're not. Life's hard. Imagine it's positive. What do you know?
it goes through it after.
So it's so. Okay. Does it only go through after this? You could actually come down like that. So there's an even number of crossings here. But you know there has to be a 0 through here. So you go to the 3/4, and let's say it's negative, and now you know there's a 0 between here. So every time you iterate, you decrease the uncertainty of where the 0 is by a factor of a half. Who here is good with their Greek or Latin? This is a liberal arts college. It's got to be somebody. Nobody? How many orders of magnitude is it to go from mega to giga?
Oh, 10 to the 3rd.
10 to the 3rd, which is 1,000. How many megabytes are in a gigabyte?
There's like 2 definitions.
There's 2 definitions of how many megabytes are in a gigabyte. What's the correct definition? And I was like, which way does my professor lean? You say wrongly and you will feel my wrath. What is the correct definition of how many megabytes are in a gigabyte?
10 to the 3rd.
You sure?
Oh, I did the wrong way.
You sure?
No.
Like a mathematician would probably say it's 10 to the 3rd. And,
You sure? What is the other option?
2 to the 10.
2 to the 10. So which do you think a mathematician would prefer? To preserve these words from either, I don't even know if it's Greek or Latin, some dead society, or the beautiful power of 2 with computers built, I'm not trying to mislead you or lead you in any way, shape, or form. The computers have on, off, yes, no, true, false, 0, 1. Do you think we'd preserve these words in the purest sense, or do something that works really nicely with powers of 2, which the computers are based in?
Powers of 2, I feel like that's the answer, but still, isn't that...
But still, no, just stop. There's no need to say the but still.
Alright, we're just throwing it out.
Before the but still. 2 to the 10. That's how many megabytes are in a gigabyte. And if you actually look on a lot of programs, when you're downloading a legal file that's large, it will say how many megabytes it is, and then right before it gets to gigabyte, it will often go to like 0.99 gigabytes. Now, 2 to the 10 is 1024, which is approximately 1,000. And that's why this isn't so bad. It's only up by like 2.4%. But it's more convenient to work with things in powers of 2. Now, what does this mean? It means essentially every 10 iterations of divide and conquer gives you 3 digits. 10 iterations basically give you 3 more decimal digits. So if you want to calculate something like the square root of 3, every 10 iterations will give you another 3 decimal digits. It's not horrible, but it's not going to make me a math major. Newton's method, I mean, this was the dividing line. Now here's those all caps. So we were using Rudin's Principles of Mathematical Analysis. It's sometimes called Baby Rudin, sometimes called the Little Blue Book or the Blue Book. I still remember it was problems 316, 317, 318. 316 was Newton's method for square roots. 318 was Newton's method for pth roots. 317 was just another way to calculate roots quickly. Newton's method destroys this. Now, what does divide and conquer use? Divide and conquer uses f as continuous. Newton's method, f is continuous, f is differentiable. So I'm going to assume a little bit more. And you can hopefully see now why we're doing this after having just done Markov versus Chebyshev. The goal is to show you how additional information can often be tremendously magnified in terms of the power. So it works as follows, and this is a nice way to review calculus. So let's say I give you the function f of x is x squared minus 3. So it's not hard to find the roots. What are the roots?
Plus or minus square root of 3.
Okay, and what is the square root of 3? You just gave it a name.
Okay. 1.4 or something.
It's actually a little higher than
1.6
1.4.
on
Higher than 1.6.
1.7.
Yes, it's a little bit higher than 1.7, but at least 7 is the next digit. I mean, doesn't everybody know that the square root of 3 is 1.7320508759352744634150587236694227?
Yes.
No, the last digit is 8. I learned that one from my daughter. All right. Just to warn you, we may have something later this semester involving pi, so you might want to study your pi. So just because I call it square root of 3 doesn't mean I know it. I want to approximate the square root of 3. Now, this function is not that hard to differentiate. Its derivative is just 2x. So here is the square root of 3. Down here is the square root of negative square root of 3. And the function, it looks something like this. Can somebody give me a bad approximation to the square root of 3? Not horrible, but not really good.
1.
You're a little bit better than 1. You mean you?
1.7.
No, 1.7 is too good.
2.
2. So I'm going to take as my initial guess 2. I think you will all agree that 2 is not an outstanding guess for the square root of 3. I just want to make sure that I'm not being accused of rigging things. Okay? So here's how it works. Here is 2. And then what you do is you calculate the tangent line to the curve at that point. And you approximate the tangent line, you approximate the curve with the tangent line. This is essentially all calculus. You take a complicated function and you replace it with the tangent line. And we see where does the tangent line hit. And we will call this point x0. What do you think we'll call this point? x1. And then it's lather, rinse, repeat. Then you go up here, take the tangent line, and you keep going. And so the question is, how quickly does this sequence converge to the square root of 3? So let's imagine we have xn. So the point is xn, f of xn. I need to construct the tangent line. So here's my point. Here's my slope, f prime of xn. So one of the reasons I'm doing this is a chance to review some calculus and some math you've seen before. You know, whenever possible, I like to review things that you hopefully have seen. So do you remember the equation for point slope for a line? So y minus the y point, f of xn, equals
slope
the
times
slope,
x minus x.
f prime of xn times x minus xn. Well, it's actually very nice. We know what f is, we know what f prime is. So we can keep doing some algebra. So we get y minus f of xn is xn squared minus 3 equals f prime. Okay, f prime is going to be 2xn, x minus xn. So this is the equation of the tangent line. Now, what is true when we get an x point xn plus 1? What is the y that corresponds to that? 0. So at x equals xn plus 1, this implies y equals 0. So we get 3 minus xn squared is 2 xn plus 1 minus 2xn squared. So if I bring this over, I get xn squared plus 3 equals 2xn plus 1. So you get xn plus 1 is equal to 1/2 xn plus 3 over xn. And there is a nice formula for your next value. You always want to check and see, is the formula reasonable? Can anybody give me a good value of xn to try? There's a natural candidate.
3.
Not 3, but you're close. You're off by 2 syllables.
2 syllables.
Yes. 3. Or 3 syllables if you want to use the word of and speak nicely. Square root of 3. Right? If we put in square root of 3, we have square root of 3 plus 3 divided by square root of 3. What's 3 divided by square root of 3? So you get twice square root of 3, and you take half of that, so you get square root of 3. This is no shit, right? If I start off over here, right, what's my error? 0. I should get back to where I started. So if I ever happen to be at the root, this is good. The question then is, how rapidly does this converge? So if it doesn't converge that rapidly, then divide and conquer wins. If it converges very rapidly, then we have Nugent's method with Luna. Now there's a lot of games you could play. One of the games you could ask is, if I choose a random seed, which point do you think I'm going to go to? So which points do you think are going to converge to square root of 3? So if I start off with 2, the hope is that if I keep iterating, I will converge to square root of 3. What other things do you think might converge to square root of 3?
I feel like anything positive.
So in fact, you could prove anything positive converges to square root of 3. Building on that, what do you think converges to negative square root of 3? And what do you think 0 does?
Like what it was.
Yeah, 0 is like, well, so we have some algebraic issues here. And if you actually look at what's going on here, the derivative is 0 at 0. It's going to be unchanged. And so if you're 0, it doesn't converge to either root. What you can do is you can look at a generalization of this in 2 dimensions, where you allow complex roots. And this is where a lot of chaos and fractals come from. So just briefly, if you look at x cubed minus 1 equals 0, this has 3 roots. And if I look at them, one of the roots is going to be here at 1, and then you'll have 2 other roots, forming an equilateral triangle where this is 120 degrees. And it breaks the complex plane naturally into 3 regions. The regions that's closest to 1, the region that's closest to this, the region that's closest to this. Which points do you think converge to this one?
Anything on the right side?
Well, anything on the right side, some of these points are actually going to be closer to this one. So which do you think converges to this? So this whole thing here is 120 degrees. Which do you think is going to converge to the root 1?
Would it be anything within the range of the 120 from the x-axis on one side?
So how far can I go like this?
60 degrees?
Yes, 60 degrees. So it's very natural to say 60 degrees. And so all of these points here will be closest to 1. Most of them will converge to 1. But there will be incredibly strange behavior near the edges, where some of these points here will go to this one, some of these points will go to this one, and some of them will go to this one. You do not necessarily go to your closest. If there is time at the end of today, I will show one of the videos, and I'll just load it up. What I want to do now is I want to just write down some values. So the square root of 3 732 0508 07 5688 779 352 7 352 744. That should be enough digits. Okay? My first guess was 2. Okay? Not bad, not great. One of the things that is worth noting about the Newton's method is you always get a rational answer if you start with a rational root as a rational guess. So if we play it the next time, we start off with 2. We get 1/2, 2 plus 3 halves. 2 plus 3 halves is 7 halves, so we get 7/4. Anybody know what the decimal of 7/4 is?
1.75.
1.75. That's not terrible. You know, I see some nods. Not bad. Let's go a little further. x2, when you do it, you get 97/56, which, as everybody knows, is, I should be looking down with pause if I say 1.7321428. That's getting 3 digits. x3, I do this again, and I get 18,817 over 10,864. That's 1.732 050 81001. So I have 07 over here. I have 10. That's not terrible. It's looking promising. Let's do one more. There's a little bit of space left on the board. Yeah, I have time to write it down. 708,158,977 over 408,855,776. And that is 1.7320508. I know it's got to start the same way. 075688. And I stopped having it right after that point. Every time you apply Newton's method in a situation like this, it actually doubles the number of decimal digits you have. So, doubles decimal digits. For most of your calculators, this is probably more digits than a lot of calculators will display. And there's no need to even write anything further than that. We're getting that with just 4 iterations. So we go from 1.75 to now we have 3214 versus 3205. That's not by too much. Then even further, then even further. You're doubling your accuracy every iteration. This is destroying. I mean, it's not even close. Right? 10 iterations of divide and conquer gives you 3 digits. So you work hard and you get, it's 1.732. Oh, you want another 10 digits, another 3 digits. 1.732050051 would cost you 20 iterations of divide and conquer. So 10, 20, 30, 40 iterations to get here. 4 iterations to get here. And it just gets worse the further you go. The amount it wins by is just unbelievable. Okay. So we have, let's end the class by just seeing some complex games. Now, I'm not sure if it is true for this one. A lot of them, it seems mandatory to have cheesy music. So we'll find out if this one actually has the cheesy music as well. This will almost surely not record. Is it showing up? Yeah, okay. Okay. So here is the polynomial, basically, x cubed minus 1 equals 0. It has 3 roots, 1, and then 2 other complex conjugates. So coloring them red, blue, and green. And then we're going to color every point in the complex plane blue if it goes to blue, red if it goes to red, green if it goes to green. Is there any point that you think is not going to go to any of the roots? The middle, so 0. So 0, if I've done things carefully, my arrows approximately, will not be colored. Everything else will be colored. And let's see what happens. And then it's zooming in. Oh wait, this might be slightly different. I mean, it's approximately the same, but okay. Okay, so here's one with 3 different roots. The other one was having some parameter vary, and what we're going to do is we're going to zoom in. But what you can see is over here, most of the points within this 60 above and 60 degrees below, most of them do go to the green as you would expect. Most of the ones 60 above and 60 below, and the corresponding to the red go to the red. But then you have this strange behavior near the boundary, where these points here are closer to the green, but they go to red. These ones are going to the yellow. And as you zoom in, as you're choosing what to go on, it's incredibly interesting behavior. This is extreme sensitivity to initial conditions. So if you've seen any of the papers on weather, where they try to model the weather, if you have a small change, you might have heard of the butterfly effect. If a butterfly flaps its wings, then this can cause a tsunami in Japan. So some people say, okay, let's find this butterfly and stop it. But the problem is the calculations, the system of differential equations you have to solve are extremely complicated. That's why it's interesting which ones are being played now. And so when it was first discovered by Lorenz, he was looking at a very simplified model for the environment. And he found something that was interesting. He wanted to look at that again. So rather than going through all the stuff up to that, he just wanted to start the calculation again from that point. So he had his printout, and he put those values in as the initial conditions, and very quickly he got wildly different behavior. And the reason was the computer was storing all data internally to 6 digits, but his printout only had 3 digits. And so when he was doing that, it was off by a little bit. So you can't talk about fractals without mentioning the Mandelbrot set. So for those of you who really like it, this one is, I think, that's good. All right. This is, we get 2 ads? What? This is 1 hour, 57 minutes, and 42 seconds. So this is, you're starting off at the very beginning. So as I told you, they like to have funky music. But it goes on and on and on. And as you zoom in, you can see the same behavior again and again and again.
37. Yeah, that makes
The Mandelbrot. So I will send the links. And so it is remarkable, the mathematics that goes. All right. This is a good place to stop.